So a few other things that we can do with Euler's identity have to do with the fact that e to the I theta. So first of all, let me say a few things. Another way to parameterize the circle is to use, this is basically the same as what we did before where we had cosine t plus I sine t when we were talking about paths, but you could parameterize the circle this way. I think that's a very useful thing to keep in mind. This allows you to change the direction of the parameterization that you want. So if you wanted to change it, you would just change the t to a minus t, and then that would reverse the order of the parameterization. So, and then you can change the values to be whatever you want. And so that was kind of an issue that I was skirting around before, but there we go. A few other things that are useful when we talk about the nth roots of unity. We now have a new way to think about the nth roots of unity because we have a new way to think about the unit circle. So the nth roots of unity are just the n solutions to the equation z to the n equals 1. And what we can do is if we can think of these solutions as the equally distributed points on the unit circle containing the number 1, it turns out that these are going to be all numbers of the form e to the 2 pi I k over n, where k goes between 0 and n minus 1. So what will happen is when k is 0, you get 1 plus 0 I. When k is 1, you're going to get e to the 2 pi I over n. So that's going to be whatever 2 pi, so 2 pi is all the way around. 2 pi over n is going to take the 2 pi radians and slice them into n equal pieces. And that's exactly what we want for the nth roots of unity, right? We want the n equally distributed points. That was a bad picture because it wasn't symmetric, but you get the idea. You want the n equally distributed points around the unit circle from 0 to 2 pi. And then, of course, we're going to stop. When we get to k equals n, we will get e to the 2 pi I again, which again is this point. Okay, so we don't need that. So here's n distinct points on the unit circle, all satisfying z to the n equals 1. And you can check that if you were to take all of these numbers and raise them to the nth power, you will get e to the 2 pi I k, where k is some integer, and therefore you'll get 1 plus 0 I, or just 1. Okay, so this is another way to think about the nth roots of unity. One other really nice thing to think about with Euler's identity is that you can now forget trig identities. This is a much superior way, a far superior way to talk about trig identities. For example, there's the trig identity where you have the sum of two angles, so sine of theta 1 plus theta 2, and we actually used it to talk about some properties of the Euler's theorem, or Euler's formula, I should say. But what we can do is we can actually now go backwards and use Euler's formula to talk about trig identities. You don't have to remember trig identities anymore. And so what I mean by this is that if you were to take e to the I theta 1 times e to the I theta 2, what would happen would be that you would have, so you would have, what is this, cosine of theta 1 plus I sine of theta 1 times cosine of theta 2 plus I sine of theta 2. And so you get some formula for it. On the other hand, you can think of this as e to the I theta 1 plus theta 2. And so what you're going to get is you're going to have two expressions for the same thing. You're going to have, if you look at this left piece, you're going to have cosine of theta 1 plus theta 2 plus I sine of theta 1 plus theta 2. And that's going to be equal to the expression that you got on the right side, which we're just going to multiply these two complex numbers in the usual way. We'll get cosine of theta 1, cosine of theta 2, minus sine of theta 1, sine of theta 2. I need to be a little bit more compact in my drawing here, but it's okay. So plus I times sine of theta 1, cosine of theta 2, plus sine of theta 2, cosine of theta 1. Okay, and I know that that seems like a little bit of a pain to write that out, but that's much better than having to remember trig identities. What you can do now is you can just compare the real parts. Since these are two expressions that are equal, that means that they have the same real parts and the same imaginary parts. Okay, and so there's your two trig identities. So this is where you can get the trig identity that sine, I'm just going to use x and y here, so I don't have to keep writing subscripts, but sine of x plus y, let's use, let's do alpha and beta. So sine of alpha and beta is just sine of alpha cosine of beta plus sine of beta cosine of alpha. And likewise, cosine of alpha plus beta is cosine of alpha cosine of beta minus sine of alpha sine of beta. Okay, and so there's some nice trig identities that you can get from there. One other thing that you can get from the Eulers identity is if you were to write e to the I theta, that's of course what we've been talking about. This is cosine theta plus I sine theta. And if you were to think about e to the minus I theta, this would be cosine of minus theta plus I sine of minus theta. And then we know that the real valued functions cosine and sine, well, cosine is even. So this is cosine of theta. Sine is odd, so you can bring the minus outside. And so what this tells you is that if e to the I theta is cosine of theta plus I sine of theta, then e to the minus I theta is cosine of theta minus I sine of theta. And in particular, if you were to add these two equations together, what you would get would be e to the I theta plus e to the minus I theta is equal to 2 cosine of theta. Or if you were to divide both sides by 2, you would get cosine of theta is e to the I theta plus e to the minus I theta all over 2. So this is now an expression for cosine that's actually valid where theta, even though we've kind of determined this where theta is a real value, theta can actually be anything that you want. So in general, cosine of z, so what I'm trying to say is that cosine of z is e to the iz plus e to the minus iz all over 2. This is what cosine of z actually is. You can define cosine this way, and this is the derivation here. Okay, you have these two expressions. Similarly, if you were to take the top expression minus the bottom expression, so in other words, subtract the bottom one from the top, you would end up with an expression for sine. I'll let you fill out the details here, but sine of z is going to be e to the iz minus e to the minus iz all over 2I. So this is going to be an expression for sine and cosine where this expression is good for any complex number z. Okay, so this is another way to think about sine and cosine. One word of caution, just to give you, sine and cosine are not bounded. So notice that sine and cosine are not bounded in general. Okay, so if you take any complex number and plug it in, it does not have to be bounded like the real valued parts were. What can happen is that, of course, if the input of your sine or cosine, if that argument is a real number, then everything's fine. Sine and cosine will be bounded, because what happens is you'll have e to the I theta, e to the minus I theta. These are points on the unit circle. So their modulus can't be very big, right? They're bounded points. They fit inside some circle of radius r. However, if your inputs involve imaginary parts, so in other words, if you plug in a complex number x plus iy, where y is non-zero, and then what happens is when you plug in an imaginary number, these iz's become, this would be like e to the minus y, and this would be e to the y. And so we know that the exponentials in general, exponential terms are not bounded. They grow exponentially fast. They're unbounded functions. And so if you have imaginary parts that you're inputting into cosine and sine, then that allows cosine and sine to themselves be unbounded. So they're still bounded as functions when your inputs are reals, but in complex numbers, they're unbounded functions. So just a word of warning there.